Hi everyone, welcome to the Earth Science Regents Review podcast series created by the Hommocks Middle School Earth Science Department. Today we're going to be talking about divergent plate boundaries. So this is one of three types of plate boundaries on the planet. We have convergent, we have transform. This one we're going to be talking about divergent. Now divergent just means pulling apart or moving away from each other. Now there's two different ways in which you can get divergence on the planet. You can either have oceanic divergence called oceanic ridges, or you can have continental divergence called continental rifting. You notice I have two different words that mean the same thing. There are some synonyms: ridge, rift, rise, and divergent. They all mean the same thing: plates moving away from each other. Now there are some geologic features. Okay, convergent plate boundaries, crust is destroyed. Here is the baby factory for crust. This is where crust is created. Underwater mountain ranges tend to be created here. You do tend to get some volcanoes and some earthquakes. Not nearly as violent as your subduction zones, but you still get a few of them. Now this is a regions diagram that shows your plates separating. Classic diagram of a divergent plate boundary. The crack right in the middle gets filled up with magma. And then an artist's rendition of what the mid-Atlantic ridge might look like, which is a mid-ocean ridge in the Atlantic Ocean, with a big crack right down the middle of the Atlantic, separating North America from Europe, and then South America from Africa. Okay, so if we first start off with your mid-ocean ridges, these are basically found underwater. So your plates are pulling apart underwater in this case. Where the crack in the ground is going to be found, that's where your rift is going to be filled with magma, and that's really where your youngest rock is going to be found. Okay, this is the longest continuous mountain range on the planet. Okay, it almost acts like seams on a baseball as they continually go around the planet. And because majority of these can be found underwater, indicates that the plates underwater are getting bigger. Scientists call this seafloor spreading. Now, if you look at page 5 in your reference table, there's a continuous mountain range called the mid-ocean ridge. It just has different names in different locations. In the Atlantic, it's called the Mid-Atlantic Ridge. In the Pacific, it's called the East Pacific Ridge. In the Indian Ocean, it's got a couple names: Mid-Indian Ridge, Southwest Indian Ridge, and the Southeast Indian Ridge. In case you get a little bit confused, go down to the bottom of your map. Notice the key, the little zigzag pattern, and the arrows moving apart. That's your divergent boundary. So scientists had to come up with a couple pieces of evidence to support seafloor spreading. The first one's going to be the age of the seafloor rock. Because magma is going to be found right at the ridge, that's where the crack in the ground is going to be. Okay, that's going to be the location where your youngest rock is going to be found. Brand new rock is found right at the rift, right where the crack in the ground is going to be found. So youngest rock is going to be at the ridge, and as you get farther and farther away from the ridge, it tends to get older and older and older. So very important to know the age of rock in relation to the ridge. You also have something called the reversal of magnetic polarity. Our Earth has an invisible magnetic field around it. We know that because when you walk outside with a compass, your compass needle points north. Okay, this is all caused by the Earth rotating and the fact that we have a liquid iron and nickel core. For the most part, we have a liquid outer core and a solid inner core, but that core is going to rotate with the Earth. It's going to create that magnetic field. Well, we know that magma comes to the surface. It's going to contain magnetic minerals. So what scientists have been able to find out is that the minerals in the rock, when they solidify into rock, will lock in the polarity at the time of formation. So most of our rock we have on the planet is going to have dominant magnetic north polarity with the minerals. But scientists have found certain areas on the bottom of the ocean floor that have rock that have dominant south polarity, which gives an indication that at one time our magnetic field has flip-flopped. It has turned upside down, where instead of having dominant magnetic north, at times we have dominant magnetic south. So this has provided evidence, the rock itself has provided evidence of possible magnetic reversals with our poles. And it provides some sort of proof that we've had some flipping of our magnetic fields. Now, over the past 330 million years, scientists believe we've had about 400 of these reversals. And it's all about looking at the polarity within the rock itself. So what you want to look for is you want to look for the pattern on both sides of the ridge. You notice right at the mid-ocean ridge, you have normal magnetic field. And as you go east or as you go west, it alternates in different zones. So it's going to go normal, reverse, normal, reverse, normal in both directions from the ridge. And that's going to indicate that as our seafloor spreads, the new magma coming up is going to lock in the polarity at that time. Sometimes it's normal, sometimes it's reversed. Here you can see not only the age of the rock, newest rock is at the mid-Atlantic ridge, oldest rock is furthest away, but you also see the different zones. You see that you're starting out with a normal polarity, and in both cases you're going to go side by side. On either side of the ridge, it's going to go an alternating pattern. And you notice that they're mirror images of each other. They're the exact same pattern because your ridge tends to diverge at roughly the same rate. Continental rifting. Well, there's two locations where the continents are splitting. One is Iceland, and one is the East African Rift. There's two locations at the surface where divergence is actually taking place. And you can see here's a picture of Iceland. You see part of Iceland is part of North American plate traveling west. Part of Iceland is on the Eurasian plate traveling east. There's a big crack right in the middle. So every time the Mid-Atlantic ridge splits, Iceland tends to get a little bit bigger, tends to get bigger earthquakes and volcanic eruptions. And here's the East African Rift. You can see the Arabian Peninsula is moving in a northeast direction away from Africa, and you have a very big section there. You see the arrows moving away from each other, a big chunk of the eastern part of Africa that's moving to the east. So very important to understand where those two divergent zones are going to take place on the continents. And again, page 5 in your reference table, you have Iceland in the middle of the Atlantic Ocean, and you also have the East African Rift Zone. Okay? That's it for now. We'll talk to you soon. Thanks so much.